So, in third part of the strength of structure and material interview preparation, so let's talk about the Mohr circle and their significance. So, what is Mohr circle and why do we need it? Mohr circle is nothing but a graphical presentation of the stresses induced in the oblique plane. It is an efficient method to understand the stresses and the shear stresses in the material in a graphical way. So for example, if we have such a material and this is the oblique plane BC dash, and we want to know the normal stress and the shear stress in this plane, so we can actually plot it in this figure. So from this figure you can see that uh, the um, the tensile stress is basically noted out here, and this every point in this circle represents a plane here. So if this the tensile stress is the highest thing, then the tensile stress will be sigma 1, and the lowest tensile stress will be sigma 2. In sigma 1, sigma 2 are basically the principal stresses. Also, this point refers to the principal plane. In principal plane, the shear stress is 0, and from this graph we can basically see that this we are actually assuming that the tensile stress here sigma x is greater than sigma y in this case, and for this plane AB we can see that this is plotted here. If this point represents the this plane, and it shows that at given angle delta angle, the angle here delta t, when it is represented in the Mohr diagram, always you have to refer to it to delta t. So basically from this plane, this AB plane, if we want to see the normal stress and shear stress, we have to make 2 delta t angle, and then we can plot the point here. So when we plot the point here, if we see that we will get the normal stress, and here along this we will get the shear stress. Okay, always the principal stresses are perpendicular to each other. Same way the axial stresses will be perpendicular to each other. So as you can see, the angle between the delta x and delta y is 90 degree, but in this Mohr circle the delta x delta y is 180 degree, that is 2 times the angle. Okay, so we can actually calculate the radius of the circle as sigma 1 minus sigma 2 by 2 with respect to the principal stresses, and this is basically the radius of the circle, also the maximum shear stress. The center of the circle can be calculated as sigma x plus sigma y by 2. Okay, these simple mathematical calculations. Next, why always the center of the Mohr circle is placed in the x-axis? Why is always in the x-axis? Why not above? So let's take, if it is in the not in the x-axis but above this, what we can see that the principal plane will also contain the shear stress. This is the principal plane, so these are the principal stresses. This also contains the shear stresses. So, but by the definition of the principal plane, it is not possible. Therefore, to have the principal plane which doesn't have the shear stress, in that case definitely the center of the Mohr circle must lie on the x-axis, that is the shear line. Okay, and also we can also calculate the radius of the Mohr circle by this calculation. So if we have a Mohr circle, then we know this distance and this distance, we can just calculate it and get the radius and the radius of the circle. Okay, what does the point on the Mohr circle represent? So every point on the Mohr circle represents a plane, which actually also helps us to calculate the normal stress and shear stress of that particular oblique plane. Okay, what does the point inside the Mohr circle represents? Nothing. Inside the Mohr circle, it doesn't represent anything. It is a meaningless thing. Okay, what does the area or perimeter or the radius of the Mohr circle gives? If you have a area or perimeter, from this we can calculate the radius, and we know that the radius of the Mohr circle is nothing but the maximum shear stress. So from the area, perimeter and radius, we can basically calculate the maximum shear stress of the material. Next is center of the Mohr circle is always at the origin. How does the loading diagram describes? What can you describe from this condition if the Mohr circle center is at the origin? So there can be three cases. One is if you have a Mohr circle like this. One is that we have a compressive tensile stress, and another is compressive stress and the tensile stress. In this case, the delta x is equal to minus delta y. This is possible. we have positive delta x and negative delta y. And the other thing is pure shear stress case, and for that we will have the center at here, and we have the both the combination here. So we can have such a condition. If we have a Mohr circle at the center of the Mohr circle at the center of the origin, okay. Next one is Mohr circle for different cases. So just draw the Mohr circle for different cases. One is the just a football which has a pressure here. So in this case we can see that the material of the football will always have a tensile stress outside. That means the hook stress and the longitudinal stress, it will be same, and that means everywhere there will be tensile stress. That means the material will be represented like this, always the tensile stress. And in this case, as delta x is to delta y, the plane will be represented, the Mohr circle will be represented in a point. That means all the planes of this material will be a principal plane, and this is basically good for the ductile material because there is no shear stress. That means ductile, this is good for the ductile materials. Okay. Next case is the submerged body. In submerged body there is pressure outside. That means at given depth we can basically calculate the pressure as to rho g z, the distance. So in this case we will have the situation like this, and as both the loads are equal, we again have the negative stresses. That means we have the Mohr circle as a point in the negative side. So same condition happens here. And if you have LPG cylinder, there are internal stress. In this there will be two kind of stresses, that is hook stress and the longitudinal stress. Hook stress along the circumference and this along the perimeter. In this case we will have such a stress outward, and for such a stress case we have a Mohr circle like this. And for the thin pressure vessels, the delta S is equal to twice the sigma x is equal to twice the sigma y. Okay. Then draw the Mohr circle for the stresses at point ABC. If you have such a cantilever beam and there is a shear force applied, there is a bending stresses, that is tensile and compressive stress. At point A there will be tensile stress, at point B compressive stress, and here only the shear stress will be there. So you can see there's a shear stress in this plane will be there at point A, point everywhere the shear stress will be there, and the condition is like something like this. For such a condition the Mohr circle will be like this. For such a condition the Mohr circle will be like this. The negative of the stress will be this point, and for normal shear stress there is a simple line here. Okay. Find the center radius of the Mohr circle. If you have such a condition given, so we can easily plot the Mohr circle. At delta x is this, delta y is this, sigma x is this, sigma y is this, and shear stress is this. So easily we can plot the 100 minus 50 and the shear stress, and then easily draw this circle. And from the equation we can find the center as well as the radius of the circle. Okay. So next, draw the Mohr circle for the 3D diagram. If we have a 3D diagram, the stresses are given, we can easily plot the maximum principal stresses. We can just take the maximum principal stresses and plot the point, and then just make circles for each plane. You can easily plot that. Okay. If the material is ductile, then along which plane it fails. So as from the previous lecture, we have seen that for ductile materials, the maximum the yield shear stress is less than the half of the yield strength. This is for the ductile material, and the brittle it is opposite. So this is weak. This has a weaker shear stress capacity. That means it fails at the maximum shear stress. And in Mohr circle, we see that the maximum stress is perpendicular to the principal stress. That means delta 2 theta is equal to 90 degree. That means at theta is equal to 45 degree, the plane will fail at this plane. So from this figure, you can see that all this picture shows the plane at 45 degree of that material. So at this planes the ductile material will fail. Okay. Then next, Mohr circle for strain. So we have seen always the Mohr circle for the stress. Let's see about the Mohr circle for the strain. The same thing. We have a situation. We have the elongation of the material here. So from this we can see that the axial strain will be delta x by x. Okay. And along the oblique plane, the BC plane, if you want to calculate the normal stress, normal strain, and the shear strain, the calculation is something like this. So for the normal strain, the calculation is B dash C minus BC, B dash C minus BC by BC, and the shear stress will be this by this. So B double dash by BC. Okay. And from here we can actually for the general case we have the strain along x and y as something like this, because if you have two stresses along the axis, then this stress will create the strain here, and this stress will reduce the strain. That means we have such an expression we can understand easily from the loads, and we can get the strain, and the shear strain will be shear stress by the rigidity modulus. So from these cases we can easily plot the Mohr circle for strain, and from this circle we can easily calculate that the maximum shear strain will be epsilon 1 minus epsilon 2 by 2, and this epsilon 1 epsilon 2 are basically principal strains. Okay, thank you.